What's up, everybody? So today I want to show you how to use MATLAB in order to plot the root locus. So instead of doing that manually using the rules we've learned in the previous lecture, we're going to make use of MATLAB to do it all for us, okay? But before we do so, I just want to go back to some of the preliminaries that we've learned about in the previous lecture. One of which is the architecture we have considered so far. Now, if you remember our discussion on root locus, we had our plant transfer function, or the transfer function of the system we want to control. And then I said that, okay, well, the root locus is nothing more than a map in a complex plane of the closed loop poles that we get by applying a proportional control action, okay, to our open loop plant transfer function denoted by G of P. Okay, so here you have the reference signal plus minus the output of our plant that drives the trajectory tracking error E times control action, which is just a proportional control action. And then that gives us the control input signal U to calculate the new output from the plant. And then we had closed the loop like that. And then, just based on this basic architecture that was the underlying assumption between all the rules that we saw for the root locus construction, we said, okay, we have our open loop transfer function, G open loop, which in this case, if you neglect the feedback loop here, all you have is K, the proportional control gain, that multiplies our plant transfer function G of P, okay, like that. But then we said, okay, the root locus being a visual mapping of all the closed loop poles, it means that we needed to obtain the closed loop transfer function. Fine. Our closed loop transfer function using this feedback configuration where we have a control gain in series with the plant and then again the feedback loop closing everything was simply G open loop over 1 plus G open loop. And if you're not sure how to get that, you could just write all the signals. So Y is equal to G of P times U, U being K times error, error being R minus Y, and then you solve for Y on one side, and then you obtain the transfer function between Y and R as being the global output and global input of everything. So that was our closed loop transfer function, meaning that the system can now be represented by a single transfer function that does the mapping between this, what I call global input R, and Y being the global output. Okay? G closed loop transfer function like that. All right. But then we needed to get the poles of that transfer function. So the first thing we did was to substitute G open loop inside of it. So G closed loop. I'm going to drop the function of S for the follow-up development just to ease up the nomenclature a bit. So G closed loop, G open loop, meaning that this is K times the transfer function of our plant, over 1 plus G open loop being K plus G of P. Okay, good. Now I'm in a position to obtain my characteristic equation, which is nothing more than just the denominator of my closed loop transfer function set to be equal to 0. That's 1 plus K times GP equal to 0. All right. Now, there was also the discussion that whenever K was being set to be equal to 0, what we get is actually the poles of the open loop transfer function as opposed to the poles of the closed loop transfer function. And I'm going to come back to that notion in a second, but just for the time being, looking at that, it means that all we need in order to map the poles in a complex plane is to solve that equation for its roots. Okay? So the roots of our characteristic equation actually correspond to the closed loop poles for various k values, from 0 all the way to infinity. Excellent. And then we had looked at a particular example. Just to put that in context. Our first example we had solved the root locus for was GP equal to 1 over S times S plus 1. Meaning that just the plant itself, with no control action, no feedback loop applied to it, had one pole at the origin, the complex plane, and then one pole at S equal minus 1. But that's for the open loop or just the plant on its own. Nothing else applied to it. So then we had obtained the closed loop transfer function by multiplying this plant with a control action K, as I just did previously, because K multiplies GP. I produce a new output. We feed this back, compare that to the reference signal. That creates an error, and multiplied with K gives us a control input signal U. So we have taken that, obtained the closed loop transfer function, and looked at the characteristic equation, just like what we did here. And we had obtained for that specific example a characteristic equation that was S squared plus S plus K equal to 0, if you remember the example we did together. All right, so that gives us the poles of the closed loop transfer function, because this again is characteristic equation of G closed loop obtained as being G open loop over 1 plus G open loop, and G open loop being our gain multiplying the plant transfer function. Essentially, solving for the roots of that give us the same thing. The closed loop poles for various K values. But how does that relate to the open loop position when K is equal to 0? Well, look, if you take that and you set K equal to 0, I'm going to do this work in this little box here, running out of space. You want to say if K equal to 0 in that equation, you get S squared plus S equals 0 for the characteristic equation evaluated specifically at this point here. Or in other words, S times S plus 1 equals 0. And obviously that gives us two poles. One pole at the origin of the complex plane, and another pole at S equal minus 1. And look at what we had to begin with just the plant on its own in an open loop fashion. One pole at the origin, one pole at S minus 1. Exactly the same thing. And that's why I said back then that the root locus is a visual representation of the poles at, well, starting from K equals 0, those correspond to the poles of the open loop transfer function, all the way to infinity. So as soon as the K value for the open loop gain that multiplies the plant transfer function is increased beyond 0, you don't get the open loop poles anymore, you get the closed loop poles. All right? So an obvious solution to use MATLAB to obtain a root locus is simply to calculate or to first obtain the characteristic equation of the closed loop transfer function and then varying the gain k for that characteristic equation, and for each iteration for k value, obtain the new roots of that equation. And those roots will correspond to the closed loop poles whenever k is set to be larger than 0. At k is equal to 0, you get the starting point of the root locus, which is what you had originally with just the plant. Same thing. Okay? So let's go to the computer. Let's use MATLAB and let's brute force the calculation of a root locus by calculating the roots of the characteristic equation for this specific example for each value of k considered from 0 to some large values. And let's map or let's plot those roots inside the root locus, and let's compare that to the hand-written solution we came up with in the previous lecture. That's the first thing we're going to do. Then we'll ask ourselves, is there a better way to do that using MATLAB? And the answer is obviously yes. Otherwise, I wouldn't be asking you that question. Okay? And that solution simply uses the MATLAB built-in function known as rlocus. So rlocus being a MATLAB command that you can use will draw the root locus automatically for you. But first thing first, let's brute force the calculation by obtaining the characteristic equation, solving for its roots at each value of k that we're going to consider. All right, so let's go to the computer and let's do that together. Here we are in MATLAB, and as mentioned on the whiteboard discussion, we're going to use that software to create the root locus for us instead of doing it manually, following all the 9 rules we saw in the previous lecture. So, first things first, I always like to start any programs I write in MATLAB with the CLC, close all, and clear all commands, which respectively clears the command window from any typed commands. We'll close any open figures, and we'll clear any variables we have in the workspace. So it's just a neat way to start fresh, essentially. So as mentioned in the whiteboard discussion, the first method we're going to look at to create a root locus using MATLAB is the brute force approach, which simply consists in solving the roots of the closed loop characteristic equation at various gain values. So to do that, we'll first create a new figure, and then we're going to say hold on, so that we're going to give us the ability to plot multiple poles for each gain value at each iteration on the same figure. So let's start the for loop within which we're going to do the calculation of the roots of that characteristic equation. So k beginning at k equals 0, or in other words, at the open loop pole locations. Then we'll start increasing our gain value, say with 0.05 all the way to 0.6. It's going to be sufficient to see the general behavior of the root locus for the first example that we've looked at. Okay, and then I'm going to end my for loop right away so that I don't forget about it. So the first thing I want to do is to define the coefficients of the polynomial that corresponds to our characteristic equation of the closed loop transfer function. In our case, it was s squared plus s plus k, to remember the example. Based on this polynomial, what I'm going to do now is find the roots, or the poles, in that characteristic equation. I'm going to simply solve for the roots using the MATLAB command roots. Easy peasy. So just to add a bit of comments here, these are the coefficients of the characteristic closed loop characteristic equation in the form of a polynomial. All right. So here we're then calculating the closed loop poles. And next, I'm going to plot the poles, first by obtaining the real parts of the poles. So poles CE versus the imaginary components of my poles, or the roots of my characteristic equation. And I'm going to plot them with little stars. So that's X. And instead of using the default color, which is blue, I like to use black. So K for black, X to specify that I want the poles to be visualized as stars on the plot. All right, next I'm going to set my axis so that I see what's going on. I'm going to use minus 1.2 to 0.2 along the x-axis and minus 0.6 to 0.6 along the y-axis. I'm going to add some grid to better visualize the data. I'm going to set the label of the x-axis to be the real components of my poles, and the y label simply be the imaginary component of my poles. Next, I also want to better visualize the location of the open loop poles, or the location of the closed loop poles evaluated at k equal to 0. This is exactly the same thing. So for that, I'm going to simply specify the poles of my open loop system, the open loop, as being one. If you remember, we had one at the origin, so 0, and the other one at s equal minus 1. So just to be explicit, these are the open loop poles, or in other words, closed loop poles evaluated at k equal to 0. So that would be the starting point in the root locus. And of course, I want to plot them using the same strategy as we've used before. So plotting the real parts of all the poles, the open loop transfer function, versus the imaginary part of my poles, open loop. And this time, to distinguish them from the closed loop poles, or whenever k is larger than 0, I'm going to plot them with red stars, like that. I'm going to add a legend to better visualize the data. Let's say evaluated for k equal to the current value of k within this for loop. I'm going to turn this variable, which is a num, into a string using the num2string command of this particular variable k. And then I'm also going to specify that for the other piece of data corresponds to the poles whenever k is equal to 0, and that will be for the open loop poles. All right. And then give us some time to visualize what's going on. I'm going to pause for, say, 0.5 seconds between each iteration. And that should be it. So let's see how it looks like. There you go. So you see that as we increase the gain k, the poles move from their original location that corresponds to the open loop pole location at s equals 0 at the origin, and the other one at s equal minus 1. And as k increased from 0 to, in this example, 0.6, we saw both poles smashing into each other, one flying off vertically all the way to the top, and the other one flying down at the bottom like that. And that corresponds to what we saw when we solved the root locus manually by following the 9 rules. It's just a very efficient way to do it. All right? So I hope that makes sense. But that's the brute force method. The second strategy is not to solve for the roots of the characteristic equation manually, as we've just done using a for loop, but instead, now we're going to draw the root locus via MATLAB's built-in command known as rlocus. And if you think that the first strategy was an easy solution, wait till you see this one. So MATLAB rlocus command. So how does that work? So let's find out. MATLAB rlocus help documentation. Let's have a look together. All right, rlocus. Rlocus plot of dynamic system or of transfer functions, same thing. So rlocus sys. So what is sys? Sys corresponds to the plant transfer function denoted by G in the block scheme diagrams. In our case, this is the plant transfer function that we've denoted as G of P thus far. So all we need is to specify the plant transfer function, and automatically what this tells us is that root locus would close the loop for us. So we don't even need to worry about manually calculating the closed loop transfer function, finding the characteristic equation, and things like that. All we need to specify is the plant transfer function. So that is beautiful. Okay? So rlocus of sys calculates plot and plots the root locus of the CISO, which stands for single input, single output model sys. That's just what I've described. Take note that single input, single output only means that this is a system that can be modeled using transfer functions, and that's what we've been doing so far. This is in opposition to MIMO systems, which would stand for multiple inputs, multiple outputs, where you would need to use state space representations to model such systems. But that's beyond the scope of this lecture. Okay, but wait. Look at these architectures that MATLAB rlocus command assumes. None of them corresponds to what we've assumed so far, where the static gain K is in series with the plant transfer function G of P. So instead, MATLAB rlocus function assumes that this gain is in a parallel configuration with the plant. Ooh, is that a problem? Well, let's go back to the whiteboard and analyze that further. All right, so let's find out together if using the MATLAB built-in function rlocus would create some issues or problems, because as we've just seen together, the architecture that our approach assumed in the past and what MATLAB assumes as the underlying architecture behind the root locus MATLAB function, then there's a discrepancy. So let's have a look at that. Our architecture, as always, is the reference signal being compared to the plant output. That creates an error. The error is being multiplied by some proportional control action. That creates a control input signal. This is being fed to our plant transfer function, G of P. That creates a new output signal denoted by Y and Y over here. On the other hand, MATLAB assumes the following. You have the reference signal, plus minus, you have the error, but then the error is being fed directly into the plant transfer function to create a new output. This output is being multiplied with the proportional control action K, yet not in the open loop or the direct path as we've assumed here. It is not in series, but rather in parallel. So is that an issue? Well, let's find out. Here, if you look at the open loop transfer function, we have K times G of P. But as I've just mentioned, on this side, the open loop is simply G of P, because the control action is not in series with the plant transfer function. So right away, we know that there's a big difference between both architectures. Now, if we compare or calculate the closed loop transfer function, whenever we had this kind of series arrangement of transfer functions being multiplied together, we know by now that this is simply G open loop over 1 plus G open loop. Or in other words, K times G of P over 1 plus K times G of P. We've done that literally millions of times, okay? On this side though, the best way to do it, if you're not sure, is just to write out what all the signals will be equal to. And I like to start the process always with the output signal Y. So I'm going to write that Y is equal to GP times the error. But we know that the error is calculated as R minus Y times K, or minus K times Y. And now I went through all the paths, or I've closed the loop by writing this equation essentially. And now I'm in a good position to solve for the mapping between, again, the global output R to the global input R to the global output Y. Or in other words, finding the closed loop transfer function manually. I'm going to put all the Y terms on one side. I'm going to solve for it. So Y, 1 plus K times G of P being equal to G of P times R. Now, if you want the closed loop transfer function, this is nothing more. So G closed loop is being equivalent to Y over R. And that, based on that equation, is simply given by G of P times 1 plus K G of P. Closed loop transfer function for the MATLAB architecture behind the rlocus function. Compare that to our closed loop transfer function obtained based on our architecture that we've used throughout this course. Gee, it's not looking good. Well, it's not that bad, because if you compare what matters, and what matters is not the transfer function, but the characteristic equation. Characteristic equation of G closed loop is going to be equal to the denominator of the closed loop transfer function. So 1 plus K G of P, always equal to 0. And if you look at what we have here, characteristic equation of G closed loop is going to be the denominator of our closed loop transfer function for this specific architecture. So 1 plus K G of P equal to 0. And this is like magic, right? Because although the open loop transfer functions are different, compare this to that, they're not the same. And although the closed loop transfer functions were also different, turns out that the denominator of both closed loop transfer functions are exactly the same. Or in other words, the characteristic equation of both architectures is exactly the same. It's 1 plus K G of P, 1 plus K G of P equal to 0. And that means that the roots of those characteristic equations are going to be exactly the same. Or in other words, the poles of the closed loop transfer functions will be exactly the same in both situations. So the answer is yes. We can confidently use MATLAB rlocus function, even though the built-in architecture that MATLAB assumes whenever we type rlocus is different than what we had used so far in terms of constructing the root locus manually by going through the 9 rules. All right, good news. So let's go back to the computer and let's let MATLAB do the root locus for us by using the rlocus command. Let's do that together. Okay, so we're back to MATLAB. As we've seen on the whiteboard, using the rlocus command is not an issue at all, although the architectures are different. So let's use the rlocus command to draw the root locus for us. Let's see how easy it is. So as we've discussed, all we need to specify is the plant transfer function g of p. And the way we do that, as you know, in MATLAB is by specifying the numerator as a polynomial and then specifying the denominator as another polynomial. And in our case, our plant transfer function was simply 1 over s times s plus 1. Or in terms of polynomials for the denominator, this is s squared plus s plus 0. Okay? Now that we've defined the numerator and denominator of our transfer function for the plant, we need to create the proper transfer function out of these two pieces. And we do that by using the MATLAB built-in command known as TF for transfer function, using the numerator and the denominator of that transfer function. And then all we have left to do is to use we're going to create another figure and to use the rlocus command based on our plant transfer function that we've denoted as g of p. If you go back to the MATLAB rlocus documentation, this is referred to as the sys variable. Okay, so again, what it does is that backdoor MATLAB would close the loop for us and apply a static gain k to our transfer function and let k increase from 0 all the way to infinity and plot the poles of the resulting characteristic equation, or the roots of the resulting characteristic equation at each iteration of the gain. So essentially, rlocus does this job for us. So we don't even need to worry about specifying the characteristic equation, extracting the roots, plotting them, and so on and so on. A single command, rlocus, does it all for us. So let's see how it works. So this is the brute force approach again. Versus the rlocus command. And as you can see, both approaches give the exact same results, obviously. All right, it's just a neat way to quickly obtain a root locus for any plant transfer function that you can think of. What's neat about it is that you can click on any point on a root locus and you're going to get several details related to that point. For example, here I've just clicked at the intersection, gives me the pole locations exactly, gives me the gain for the static gain k that drives the pole to be at that location. At that location, that gives me the damping ratio, zeta, the overshoot in terms of percentage, and the natural frequency, 0.5. All right. So now that we've learned how to use the MATLAB rlocus command, let's go back to the second example that we have looked at in the past lecture to create a root locus manually. And again, we'll compare both methods or approaches, the brute force method and using the command. Okay. So first I'm gonna change a little bit my increment for my gain value that I want to look at. I'm going to go from 0 this time all the way to 10 so that we can see some interesting behavior of the root locus. We have to go all the way to 10 in that case. The characteristic equation for the second example, if you go back to that lecture, it was s cubed plus 3s squared plus 2s plus k. All right. Now I'm going to change my axes a little bit in terms of their limits so that we can clearly see the full root locus. I'm going to go minus 3.5 to 0.2 and say minus 3 to positive 3. Again, my labels don't change. The open loop poles in that case were 0, s equal minus 1, and s equal -2. All right. And because I have so many points in that case, I have 100 points essentially, I'm going to plot. I'm going to pause for a shorter period of time, 0.5 seconds, 0.05 seconds. Feels appropriate here. And I'm going to use the MATLAB rlocus command to do it for me. So all I need to do is to define the plant transfer function. So 1 s cubed plus 3s squared plus 2s was my denominator, plus 0, obviously. So we'll compare both approaches. So now you see that as you increase your static gain k, the poles smash into each other here and will eventually cross the imaginary axis at some values, while this pole just flies off to the left. Exactly as we've established manually when we had done this example together. And surprise, surprise, the MATLAB rlocus command gives us the exact same result, but with the added benefit that you can zoom on, say, an interesting part, being the crossing of the imaginary axis, for example, and click, and you'll get the gain value at which the poles cross this axis and become unstable. So it would be at a gain of about 6 in that case. All right. So that's about it for this short video on how to use MATLAB to obtain a root locus of any given system. So hope you enjoyed, hope you learned something, and I'll see you in the next video.